All right, so today we're going to look at quicksort, but then we're not going to actually implement it because it's already implemented for us. Instead, we're going to understand how to do searching and sorting in practice. But we do need to understand the algorithm and at least appreciate why it is called quicksort. So let me remember that what we do is we choose a pivot element and we start partitioning around it. We put everything less than it on the left side, everything greater than it on the right side, and then we recurse on the left and the right. So I'm not going to go through the entire process here, but we will look at maybe one iteration of this, or maybe a couple. Right? This is going to end up being our pivot element. Right? And remember, just like in basketball, pivot foot, once it's down, you can't pick it up. You're going to pivot around that point. So what we're going to do is we're going to look at the rest of the elements, and we'll see that 4 here is less than 42, so it goes over here. 9 is less than 42, so it goes over here. 4 is less than 42. 101, that's greater than 42, so it goes to the right. Right? Remember, we're comparing everything to the pivot element right here. Next is 34. 34 is less than 42. Right? 12, 2, and 0 are next. Now that we've partitioned around this pivot element, where does this pivot element end up? Where should we put it? Right in the center, right? 42. Now, should we ever touch 42 ever again? Nope, because everything larger than it is in the left and the right half. Everything less is in the left half, right? But what we do is we recurse. We recurse on this side and we recurse on this side. Now, tell me about the recursion that's going to end up on this side. Is there any work to be done over here when it's just one element? No, because by definition, one element is sorted. Over here, we would then choose a new pivot element. We'll just go ahead and choose 4 here, right? Let's see, let's go with that like that. And we would end up pivoting around it. So 9 is greater, 9. 4, you break ties arbitrarily. You can go left or right, just be consistent about it. And so what I'll do is I'll put 4 over here on the left, right? So ties will be broken preferring to the left side. 42 is greater, so it ends up over here. 12 is greater than 4, 2 is less than 4, and 0 is over here. Right? And then we end up putting 4 where it belongs. Okay? Then we would recurse on this left side, we would recurse on this right side. Now, as you can see from, now that would continue all until it's completely sorted. But as you can see from this example here, sometimes you will have a split that is bad. In other words, most of the elements end up on one side, and only 1 or 0 elements end up on the right side, right? Or the other side, vice versa. Sometimes you'll have a better split, where you get lucky and the pivot element of your choice ends up being optimal, that everything over here is less, everything over here is greater, and that they're about the same size, n divided by 2 and n divided by 2. Right? What choice of pivot element would be ideal then, in this case? The thing in the middle is defined as what? The median, right? The median choice, right? Basic statistics, right? Not the mean, but the median, the thing that is right dead center. And so that's the optimal choice for quicksort. You can't always get the optimal choice, although algorithmically, theoretically you can. But at the end of the day, remember that quicksort, we're not going to go through the full analysis here because it would require more math than is covered by this course. But at the end of the day, on average, it's going to make n log n comparisons. How much better is that than selection sort? Remember that selection sort was about n squared comparisons. Right? Quicksort is going to be about, again, you can't guarantee this, but on average, it's going to be n log n. In other words, they share one term here, but the other term, n versus log n, right? Those are where it's a difference. Now, we already saw how huge of a difference that makes for binary search. It's an exponential speed up with respect to binary search. It's not an exponential speed up here because we do have this polynomial term out front here, but it's still a huge speed up. How would you look at this? A couple of perspectives here. First of all, I'm not going to do the calculus because if you wanted to take the first derivative of n log n, what would you have to do? there's a rule called the product rule, and I forget about it. I don't want to go that far, right? So instead, let's look at this from the perspective of a very large array. Say that n was 1 trillion elements, right? Now with selection sort, I'll just truncate it there. Selection sort, you're going to have to make what? 10, 12, 10 to the 12 comparisons. Right? Does anybody even know what that is? That's 10 to the 24th, right? That's like quintillion or something like that, I think it is. Quintillion, question mark, all right? Now, what about quicksort? Quicksort, if I plugged in n on 10 to the 12, and then log of 10 to the 12, right? Then about how many is that? Well, what happens is that 12 right there. It comes out front, right? And you are left with, I'll keep 10 to the 12 there, times 12, times, what about log base 10? How big is that? 3 point something, right? So I'm just going to go ahead and say that it's 4, and I'll say that this is all less than or equal to 4, right? In other words, this is going to be 24 times 10 to the 12th. Right? And remember that this is trillion, so this is 24 trillion. Right? That's not that much bigger than the actual array itself. It's just 24 times the size of the array. Right? For that reason, when we say n log n, right, then we call this what's called quasi-linear. Quasi-linear. It is almost linear. Right? It would be linear if we just ignored the logarithmic term. And in fact, a lot of cases, people will do that. We won't talk about big O analysis, but there is big O and then there's a tilde above it where you ignore lower order logarithmic terms because in practice, there's almost nothing. In practice, if you've got 10 trillion elements, that term only contributes 24 to the final results. Right? So this is why it's almost quasi-linear. It's almost linear. Okay. Another way of looking at this, what if I go from n to, say, 10n, an order of magnitude larger? With selection sort, right, then you are going 100 times slower. Right? We did that analysis last time. But what if you do it for quicksort? Then you are going 10n log of 10n. Right? Now, tell me some log identities here. What can I do with that log 10n? Log of AB is equal to log of A plus log of B. So this is going to be log of n, I'll switch them around really quick, plus log of 10. Right? In other words, the highest order term here is only going to be 10n log n plus some change, right? And again, this is going to be 3 point something 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 times that, so 30n, who cares? This is the bigger one, right? And guess what? It's only about 10 times as big plus an additive term over here. Right? So it's quasi-linear again, right? It's only, if you go up by an order of magnitude 10 times as big, then you are only about making 10 times more comparisons to do this. Right? That's why quicksort is quick, right? It's not the only quick algorithm. It's, there are many algorithms that are n log n, which is the theoretical lower bound that you'd have to, like there's no faster algorithm than that, at least comparison-based sorting algorithms. There's also merge sort, there's tim sort. There are hybrid solutions of these things where you do quicksort, but you don't do it down to when until you have one element. You do it down until you have like 10 elements, and then you just switch over to some other sorting algorithm. Those are hybrid sorts, right? So there's lots of solutions out there, but we're going to now focus on, oh, come on, no, keep going, please. All right, there we go. We're going to actually look at what's built into the languages, right? Sorting in practice, basically. There is a quicksort, right? That is built into the standard library in both languages, by the way. But first of all, to be able to understand how to use it, we need some additional things here. Right? Oops. Before we do that, why am I'm not plugged in. That's why it's slowing down. starting. It's Mac OS starts to throttle you, and that's why it's really hot if you're not plugged in. So hopefully it'll get faster now. All right. So sorting in practice. In general, you do not need to write your own searching or sorting algorithms or functions. Right? Instead, why wouldn't you want to do this? First of all, it's because that it would require a lot of copy pasta, right? I want a sorting algorithm for integers, all right? Copy pasta that. I want a sorting algorithm for doubles. Now I want it for strings. Now I want it for airports, right? Like you're doing right now, right? So it would be a lot of copy pasta for each different type. Not only that, but you've got a lot of work ahead of you because you need to test it. Make sure that there's no bugs in it. Lots of debugging, right? In other words, the term that we use here is don't roll your own, right? Don't roll your own solution. And I've borrowed that from cryptography, where cryptography, you always say don't roll your own, don't create your own crypto system, because obscurity is not security, right? Just because nobody else knows your system doesn't mean that it's not crackable, right? We'll use our built-in generic sorting searching algorithms, right? And for C, that's going to mean, there we go. For C, that's going to mean qsort. Right? And for Java, that's going to mean collections.sort. Right? There's also arrays.sort, but remember, arrays suck, so we're going to be using lists, right? The built-in functionality is generic, right? In both of these languages. In other words, there's not a qsort for integers, a qsort for doubles, a qsort for airports, because there can't be, but instead there's a qsort for any type. It is written to be generic to be applied to any type. But there's a drawback to that. If I'm generic and I receive an array of stuff, right, how do I know how to order this stuff, right? How do I know that, oh, these two things are out of order, I need to swap them? Or if it's quicksort, how do I know this pivot element compared to this element over here, the element needs to go to the left or to the right, right? You need another component, and that component is what's called a comparator function, okay? Or in Java, it's just called a comparator. So we'll start out in C here, right? A comparator is a function that compares two things. Who would have thought, right? A and B, right? And it returns. Oops, we got a question online here. Okay, all right. I think it's just a comment, not a question. All right. Anyway, it has the following pattern. Okay. It returns something negative if A comes before B. It returns 0 if A is equal to B. And it returns something positive if A is greater than B, or equivalently, B is less than A. In other words, B comes first, right? So what it's doing is it's taking these two things, A and B, and are they in order on the number line? If so, it returns something negative. Note here I'm emphasizing something. It doesn't return -1, although it could. It just returns something negative. If they're out of order, then it returns something positive. And then if they are the same thing, then you're right on the origin at 0. Right? That's how I like to think about it, at least. Okay? In C, the signature of a comparator must be the following. Right? And let me go to the next line there. There we go. It returns an integer because it has to return something positive, negative, or 0. And then it takes two generic elements. Const void star A. We've seen void stars before, like void pointers before, generic pointers. Where have we seen that? There's something that returns a generic pointer to a memory location that it just allocated for you. malloc, right? Malloc returns a generic void pointer, and then you can cast it to whatever you want. You can turn it into an integer pointer, or you can turn it into a double pointer, right? In fact, we'll do that inside the function. But this is how it achieves its genericness, right? It's not going to work if they're integers. For example, if I change this to int and int, that would only be a comparator that's good enough for integers, right? Now I would have to change everything and rewrite everything if it were a double, right? I'm just going to keep it generic, and it's going to be a pointer to anything that you want, okay? It returns an integer following the pattern above, right? That it's something negative, positive, or 0. And it returns, or it takes those two generic void stars, right? Note there that there's also a const in front of it. Why? Because we're making a promise that we're not going to be making any changes in that comparator function. We're just going to be looking at A and B and say, oh, A comes before B, or they're out of order, or it's 0. Right? Now, to understand this before we start writing these, let me go ahead and give you a diagram. Okay. This is in my book, but there we go. All right. So the sorting algorithm just takes input, stuff. It doesn't know what it's receiving. It doesn't know that it's integers or doubles or characters or whatever, and it doesn't care. It knows how to it knows how to sort things. These two things are out of order, swap them, right? But it doesn't know how to order them. That's where the comparator comes in. Anytime it needs to ask, are these two things out of order? In other words, I need to swap them. It hands that question off to the comparator. The comparator responds with something negative, positive, or 0. And then the sorting algorithm knows, oh, okay, I need to leave these in order, or I need to swap them, or put it in the left partition, or put it in the right partition. Right? That's how we achieve this generic code that can be applied to any type. Okay? All right. So inside the function, you will follow the following pattern. Right? You cast the generic pointers to the types that you expect. Right? So if I'm a comparator for integers, what I'm going to do is I'm going to cast them as integer pointers. Now I can go ahead and dereference them, find out what values are in there, and then make my comparison. Right? Generally, you will set up an if-else-if statement in order to do that logic. Right? A is less than B. Okay, we'll return something negative. A is greater than B. Okay, we'll return something positive. A is equal to B. Now return something 0. Something 0. Just 0. Right? Okay? That's what we need. All right? Once we've got that, then we can call qsort. Right? Once you have your comparator function written, then you can call q. Actually, before we do this, let's go ahead and write our comparator function. Let me come up here, and let's go ahead and write a comparator function for integers. Let's go ahead and document it. A comparator for integers that orders them. Note here, I'm not saying sorts them, because it's not going to sort anything. It only takes two things. It doesn't take an array of things. Qsort does that. This is going to take two integers A and B and orders them in ascending order. Right? So in other words, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That would be descending order. Right? All right, what should it look like? Int, CMP int A, int B. Is that a comparator? No, it is only a comparator if it looks like that. It takes it returns an integer and then takes two const void stars, not integers. Right? Okay, so there. Now it is a comparator. Anything else, and it's not a comparator. Right? If you want to label this, you can label it a little bit more. Ascending. Right? ASC is short for ascending. All right? Now let's come down here and actually implement it. Okay. Hopefully I don't have a version of this somewhere else, right? Generally, we're not going to do error checking here. Check this, see that null, because you're just asking, does A come before B? Well, if you're storing null values, then maybe those have an order, right? In fact, we'll do this in Java. What if I have a bunch of integers in a list, but also a bunch of nulls in the list, which is completely allowed, right? Not that it's a good idea, but it's allowed. Right? Should nulls come before anything? Should nulls be equivalent to 0? Should nulls come after everything? Right? Those are questions that you can answer. Then, like, okay, fine, I'll go ahead and put all nulls first, and then I will put all the actual numbers in ascending order. Right? In which case, you're not doing error handling. You would actually order the nulls. Right? I won't get into that right now, though. Right? All right, so the first step that we're going to take is we are going to cast those generic void pointers as the actual types that we expect. The actual type that I expect is const int star x and a const int star y. Once I have those as const int stars, then I can dereference them and find out what values are stored in those memory locations. But to do that, I need to give them a value first. And so this will be forced to become a const int star A and const int star B. I'm forcing A, which is a generic void pointer, to become a integer pointer that I now call x. Likewise, B, it now becomes y. Right? Now I can ask the questions. If x is less than y, then return something negative. Careful, is that how you work with pointers? I mean, this will work, or it'll do something. It won't work, but it'll compile and it'll run. What you're asking is that memory location come before the memory location of y, right? And that's not what I want. I want the value stored in x. What do I put in front here in order to dereference x to get its value? It's a pointer, so asterisk, right? Or star, right? There we go. All right. Else if x is greater than y, then I'll return something positive. I could, of course, mash my keyboard here and just give it a random number, right? Keep it simple, though. -1, 1, and 0 are the best ways of doing this. Else, return 0. Right? So again, if x comes before y, then it's in ascending order, so like 5 and 10. 5 is less than 10, we will return -1. If they're switched, 10 and 5, well, they're out of order and they need to be swapped by qsort, and so I return something positive. Right? Finally, I return 0 if they're actually equal. Right? Why am I not doing this if x is equal to y? That's redundant, right? Why would you do that when you can just, I mean, that's the only other possibility is that they're equal. What if it's a double? We'll talk about that later. Right? There is my first comparator ascending. Okay. And by the way, before we do this, before we move on, how would you do it descending? I'll call desk in descending order. Okay. I'm going to copy paste this. There we go. And if this is descending, then what's the change that I need to make? That becomes greater than, and that becomes less than. Okay? Still lots of copied code though, right? What else could I do? I already have a function that will order them in ascending order, right?
Flip the output value.
Okay. So int foo is equal to cmp int ascending of a and b, right? And then I will flip the value. How do I flip the value? Return foo times -1. All right, good. Why? Because +1 becomes -1, -1 becomes +1. What happens to 0? Stays the same. Right? Now I didn't need foo here, right? What could I have done? Return just the negation of that. Right? Playing a little bit of code golf here, right? Maybe you might have said 1 times that, right? There. Now I've got it down to 1 line. Can you get it down even further? Well, you don't need to multiply it. You can just negate it. Can you get it down even further? Have you ever heard of code golf? Right? So golf scores, lower scores are better. So if you can get something with fewer lines of code or fewer characters or something, then you win. So we've got, can I get this down 1 fewer character? What if I did that? Right? I just switched them around, right? And then that's probably as far as you can go, right? Just call that function and you have to return that value, right? So little tricks there, right? Code reuse. Right? If you want it reversed, you could rename this reversed or something like that, but it's descending is probably better. But once I've got those comparators, now I can start working with qsort. Here's the actual function, and there's some new stuff here, okay? New stuff and old stuff. First of all, base is going to be my array, all right? It doesn't return anything, by the way, but base is the array of elements you are sorting, okay? NEL is the size of the array. That is the number of elements to be sorted. Because anytime you give an array to a function, you have to tell it how big it is, right? So the same is true for standard library functions as all the functions that we've been writing up to this point. Now there's something else over here. Size is the number of bytes each element takes. Hint, always use size of, right? Just like we've been using with malloc. Now, why would quicksort need to know how many bytes each element takes? Suppose that it's sorting integers, and there are 4 bytes over here for one integer and 4 bytes over here for the other integer. It needs to swap them because it asked the comparator, are these in order? And the comparator said, no, they're out of order. So I need to swap these two. What do I need to know? How many bytes I'm taking from over here and moving over here, and how many bytes I'm taking and moving over here. Because if it's an array of, say, doubles, then there will be 8 bytes over here and 8 bytes over here. I don't know, again, I'm quicksort, I don't know what they are. I don't know that they're integers, I don't know that they're doubles, I don't know that they're airports. But I do know that I need to know how many bytes there are, right? So I can take those bytes and move those bytes over here. Finally, the last one, compare, right? Oops, sorry. That's short for the comparator function that you want to use, right? For now, this is actually a function pointer. We might talk a little bit more in detail about function pointers later on, but just understand that it's a pointer. Right? Of course it's a pointer. You've got a star in front of it, right? But this syntax here is all new. That syntax is a pointer to a function. Right? It's not a pointer to a variable, right? We know pointers to variables by now, but it's a pointer to another memory location that contains not a variable, but the code for a function, right? Everything at the end of the day in a computer is stored in memory somewhere, right? So a function is stored in memory, right? Because it's got to be executed. So it makes sense that you can point to that function over there. These are sometimes called callbacks, or in this case, they're specific comparator functions. Basically, what you want to, it's a pattern that we haven't really talked about because this is the first time we've seen something like this. But JavaScript, for example, this is how you do everything in JavaScript using what are called callbacks, because it's all asynchronous. You say, all right, call that function over there, and function, when you're done, make sure that you call that function over there, right? What am I doing? I'm pointing to that function over there, right? Because when you are done, call that function back. That's why they're called callbacks, right? I don't know where back comes from, but whatever, okay? All right, let's go ahead and take a look at an example. Right? Let me come back over here, and remember, we've got our comparators. That's all we ever need to write, okay? We were trying selection sort before for this many elements, but let's go ahead and kick it back down to 10. Generate my random array here. We'll go ahead and print out the array to see that it works. But instead of calling quicksort here, we'll print it out after as well. We will instead of calling selection sort as we were doing before, rolling our own, we're going to call quicksort here, qsort for short. Now remember, the order of things that we pass in are the base, that's the array, the number of elements in it, and the size. Okay, so I want to sort array. There are n elements in there, and then each one of them is integer. It's an integer array, so it's size of int. Right? Now the last thing that we pass in here is the actual comparator function that we want to use. For that, all we have to do is grab the name, because the name of a function is its pointer. Right? So not selection sort, what am I doing? CMP int ascending. Let's come back up here. There we go. There. Okay. Let's go ahead and compile this. CSE 155H, GCC demo, and I've got a bunch of stuff in array utils.c as well. There we go. Let's run it and see that it actually works. Right. I don't know why it is taking for, yeah, what? Oh, thank you. All right, we're still doing selection sort then, that's why. Right. I guess, maybe. Let's go ahead and go demo over here. Okay, there, yeah, that's way too big. Let's go down to 10. We can get rid of that. We're not, let's get rid of selection sort here. I do want to print it out though to make sure that it works. Print array of ARR and N. Right? Then we will call QSort. Remember what is array, the size of the array, the size of each element in the array, and finally my my comparator. And because I wrote it over there, now it's gone, right? So let's go ahead and grab all of this stuff. Ascending. Sorry, I should have checked that before I came. And I'm just going to put these up at the top here. I'll fix it later when I post them. And this was ascending. There we go. And let's print it out afterwards to make sure that it was actually sorting in the order that we intended. Right? There we go. Is it an ascending order? Yeah. Run it a couple of times here. Right? Ascending order, ascending order, ascending order each and every single time. What if we want a descending order? All we would have to do is change the comparator that we're using. I didn't have to rewrite the entire algorithm. I just had to rewrite the component that the algorithm needed in order to order things. And now is it in descending order? Yep. Descending order, descending order, descending order, each and every single time. Right? Okay. Awesome. QSort. I don't have to do anything else. Right? We'll talk about binary search and linear search, the generic versions of those later. Right? But let's go ahead and take a look at what it looks like over here in Java. Okay? Java is a little bit different. Right? Java, it's going to be comparator objects, because in Java you can't have a function just by itself. In C, functions are what are called first-class citizens because you can just create a function. Right? Up here, I'm just going to go ahead and create a function. Now it's in the global namespace. But over here in Java, remember that Java, everything is a class or belongs to a class. So instead of creating a function, I have to create a class and then put the function inside of it. Right? I don't have any setup over here, but let's go ahead and go with integer. All right, foo, or list, is equal to new array list. And, well, I don't know, let's grab this stuff right here. That's lots of high numbers there. I don't know why, but we'll just go ahead and grab it. Is there an easy way of doing this? Int array is equal to, I can get it into an array, and can I array dot to list? Nope, not toString. Array dot to list? Nope. How can I easily convert an array over to a list? I can't just do this. No, that would be too easy, of course. Right? As list. So array dot as list, is it? Nope. Arrays dot as list. There we go. All right, but it's a variadic function. It's not this. There we go. All right. So I had to do it like that. If you've never heard that term before, it's a variadic list, meaning that the number of parameters can vary. I can put 11 in there. I can put 10 in there. I can put 5 in there. And it's all the same, right? If we take a look at this, the way that this is achieved is through an ellipsis, or whatever you want to call it, right? That's how you can do variadic okay, so it's probably expanding out and doing it for me. But anyway, I've got my list now, okay? I want collections.sort, okay? Now, here's the neat thing in Java. The integers, the doubles, the built-in types, those are so common that it just goes ahead and allows you to give me the list, right? Let me go ahead and print it out to make sure that it's actually working. System.out.println list, right? And copy that, and we'll see that it is just as before, unsorted, and now it is sorted in ascending order, right? That's the default. So here's where a comparator comes in. What if I want something other than the default? What if I want it in descending order? Or what if I have my own user-defined type, like, say, airports, and I need to sort it? Well, now if I had an array or a list of airports, this would not compile because it doesn't know how do you sort something like that. So what we need to do is we need to bring in another component. And I'm now frozen. Come on. There we go. All right, there we go. All right. Hopefully that's not affecting the live stream. Nope, we're still at 60 FPS. All right. All right, so what I need is a comparator for integers. Comparator, right? And integer. Right? That's the class, okay? I'm going to go ahead and import this. It's in java.util, so it's not automatically part of the language, right? And I'll call this one, just like I did the other one, CMP for integers in descending order. I'm not going to write one for ascending order because that's the default ordering. That's what Java refers to as the natural ordering. Actually, every language will refer to it as the natural ordering, ascending order. The natural ordering for strings, that's also well defined. It's lexicographic ordering according to the ASCII text tables. A's comes before B's, etc. Right? So I need to create this new comparator. Right? Okay. Brand new syntax here. We've never done this before. This is what is known as an anonymous inline declaration. My comparator, I could have put that into a class. I could have put that into a class called my awesome integer descending comparator, right? Java, right? But it would only have one use. It would only have one function in it. Right? So why even bother putting that into its own class? I'll go ahead and do it in line here. Now, what this is going to require is it's going to require me to add one method here, a compare method that takes an integer a and an integer b, right? And then it makes your comparison right here. This is where you put your logic. If a is less than b, then I'll return something negative. Right? Done. Else if, oh, by the way, this is a descending order, so what should I be returning here? Something positive. Right? Else if a is greater than b, then I'll return something negative. Right? Else I'll return 0. There. Now once I've got that comparator defined, I can go ahead and use it as a second argument to my sort call. Right? And it'll use that comparator instead. And now it's in descending order. Right? Let's play some code golf here with the last 10 minutes. I'm going to get this down really far. Right? First of all, I don't have another comparator to call, but I do have the natural ordering. A.compare to B. Right? That is the natural ordering. It's going to compare A to B, and if I just return this, by the way, as it is right now, return that, then it would end up being the natural ordering in ascending order, right? Because that's how it's built in. Once again, to reverse it, I could say negative on that. And it's now reversed. Is there a better way? B compared to A. Right, there we go. A. There we go. All right, and we still have it in reverse. Java, I can do more code golf here. Right? All right, there, as of Java like 11 or 12 or something like that, what you can do is you can build these comparators using the comparator class. Right? So I'll just call this 2 for now because I don't want to mess up the other one. Comparator, or is equal to comparator dot comparing. Right? Oh no, this is going to make more sense with user-defined types. Isn't there an int comparison dot int? Nope. Maybe it's an integer class. Integer dot compare. It's not in there. I thought that there was a comparator class. All right. Anyway, what I can do is I'll do ascending for now. Right? Is equal to comparator dot CMP int descending dot reversed. There we go. That's the easiest way of doing this for now. We'll look at an even easier way of doing this when we've got a user-defined type here. In fact, do we have a user-defined type that we can play around with? Let's go ahead and look. I mean, we've got to have something from a previous book. There we go. We're going to come back to the books here. Okay. I'm going to have to code it next time, but I'll show you how to build it now. If I use ascending, then now it's ascending order, right? So you can just take another comparator, and if you want to, you can reverse it. I thought that there was an int comparator already, and I'm sure that there is somewhere, but I don't know where it is right now, right? How would we do this for book? Right? So let me go ahead and grab all this stuff. And this is going to be a comparator, not for integers, but for book. And how do you want to order a book? Like, how do you want to sort these books? Do you want to sort them by the person, by the title, by the rating? Let's just do title at first, okay? Book by title, okay? Now, this doesn't take integers anymore. It takes a book and another book, right? Okay? Oops, no space there. Now, how am I going to compare A and B if I want to do it by title? So I'll say string A X is equal to A dot get title, right? String Y is equal to B dot get title, right? And then I can compare those, right? Except that they're already naturally comparable, right? So what I can do is I can say return, return X dot compare to Y. Right? And why are you still complaining? Comparator. Oops, what did I do wrong? Add unimplemented methods, there it is. Oh, there, book, there. All right, there we go. I had to change the parameterization there, okay? That's going to do it by title, right? Here is an easier way that I can do this. Comparator book by title. I'll rename this in descending order, right? Is equal to comparator dot comparing books get title. Is that the correct syntax? Nope, just there. There we go. So that's kind of like a function pointer like we just did in C, but it's not a function pointer. This is actually taken from, I believe, C++, or it's inspired by C++. It is a class function grabber, or selector, I guess is what they call it. If this is the class, this is a method in the class, then this is your way of selecting the method within that class, : right? So this one will be, but it's not descending because it will be naturally ordered according to strings. So then what I can do is I can reverse it. There. So what you can do is you can chain these things. Let me do one more to show you the real power of this. Right? CMP book. And I'll just call it foo right now because I don't know what it's going to end up being. Comparator dot comparing, right? Pairing. Now, how do you want to? What's another way of comparing the book? By rating. Okay, so get rating. Now that's going to be natural, right? So it's going to be lowest rating to highest rating. Okay, fine. But then what if they've got an equal rating? They're both 4.0s. Then then comparing author, book, get, let's go by title. There we go, right? There. And I don't want that, I want that one reversed. There. So, come on, there we go. So you can chain all of these things together, and generally what you do is you align all the dots, and then you can read it really, really clearly. I want to have a comparator comparing the rating, then by the title, but I want that to be reversed. Right? What if you wanted them both to be reversed? There. There. So rating would be reversed. Right? That means that the highest rated would be up here, the lowest rated would be down here. Then if you've got a tie, right, they're both 4.0 and 4.0, then you would compare the title, but then those would be reversed as well. Right? Can I do it by author? All right, so we've got the same rating, the same title for some reason, but then comparing book, get author. All right. Now that's where it fails. All right. Why? What does get author do? Yeah, it returns an author. An author is a person. Do you see anything in this class about natural ordering, about that person comes before that person? I don't. Right? So how are we going to do that? We only have 5 minutes here, but what I'll do is I will add one piece of code and then we'll continue it after the break, unfortunately, because we don't have anything on Friday. This is going to implement comparable person. There. And now this is going to be fine over here, right? It shouldn't be, yeah, it's not compiling because the other one's not compiling. But now it's perfectly okay with the author being orderable, right? Because it says over here, this author is now comparable to another author here. It's not compiling because I haven't written the code to do that. So let's add that unimplemented method, and down here, compare to. That sounds familiar. Integer has compare to. Right? The string has compare to. This is how it achieves its natural ordering. All you need to do now is to add the logic to order a person, to order two people. This person and that person. And for that, I'm going to go ahead and rename this that for now, right? Because we've got this and now we've got that. How are you going to order a person? How old they are? You could do that. Order them by last name, first name? You could do that. Order them by last name, first name, and then if they have the same last name, first name, break ties by taking the oldest first. Right? You could do all three of those things. You just need to do something here. Right now, the default is that you're saying all people are equal, right? And that's fine. It'll actually do something. It'll say, all right, these two people, they're equal, so I'm never going to swap anything, right? And that's what ends up happening in practice. Right? But otherwise, what we'll do when we come back from break is we'll add the logic there to order a person. Yeah?
Does the book then have a comparable? Or
It does not have a comparable method.
Why can I compare the books but not the...
Yeah. I mean, you can add it. Implement comparable to book. The drawback to doing this, though, is that you can only have one ordering, right? Whereas over here, if you just create a new comparator, you can have any ordering that you want.
Okay.
You basically, there's one natural ordering, right? And in this case, I would probably choose ID because ultimately what this is, it's tied to some database somewhere. And two things in a database are only ever equal if their IDs are equal, right? And so that's what I would do here. You might have an argument for doing the ISBN instead, but that's what's called a surrogate key, and that's bad practice. Right? And we'll talk about that in Computer Science 2 next semester. But otherwise, have a good Thanksgiving break, and I'll see you on Monday after the break. Right?